All right, welcome back to our lesson on perpendiculars. In this video, we'll be looking at how we can construct a perpendicular through a specific point. So before we can construct a perpendicular through a point, we need to have a line, and then we need to specify a point on that line. So here is a line, and I'm going to specify some point. I'll intentionally put it so it's obviously not in the middle of the line. I'll go ahead and call it point A. So I want to draw a line through point A perpendicular to this line right here. Okay, so yeah, I would give it a shot if you haven't tried it already, and pause the video and then come back and I'll actually show you two different methods. Give it a shot. Okay, so the first method is with an equilateral triangle, and we're going to need to start by centering the compass at A and then set it to be, pretty much any setting. You don't want it to be so big that it misses the line, and you can always extend the line if you have to. You don't want it to be tiny because then it will be less accurate. So we center the compass at point A, and then we make an arc here, and then we sort of keep the compass at the same setting, and we can continue that arc. But the key is that we need 2 points equidistant from point A, here and there. Okay, so now we have these 2 points. And now in order to construct a perpendicular, we can construct a equilateral triangle on this subsegment, the segment that connects these 2 points. So I'm actually going to do it below because I'm running out of space. I should have set my compass to be a little bit smaller. That's okay. Okay, so we can see here, if I did the equilateral up there, kind of running into my title there, but that's fine actually, either way. So picking that point or this point, either one, we have an equilateral triangle. So let's go ahead and draw that in. And actually, we don't necessarily even have to draw it in. I will, but the key is that you just connect the point, this point here on the equilateral triangle with the original point A. Oops, I didn't do the best job of that. My apologies. Okay, so what I'm claiming is that this right here is perpendicular. So that's the first construction. The second one is similar. Let's go ahead and once again draw a line. I'll draw right here. And once again, we need to pick a point on that line. And we need to set the compass to, whatever, some setting that intersects the line but isn't too small. So we draw our 2 arcs just like we did in the last one. Okay. Now this particular construction, all we have to do is we go to one of those intersection points, we make the compass a little bit longer, a bit longer than the distance from the intersection point to the point we're trying to draw a perpendicular through. We can pretty much pick any setting in here. It doesn't matter too much. And once you pick the setting, you can go ahead and draw an arc there. Then keep the compass at the same setting. Don't change it. And now center it at the other intersection point and draw the other arc. And now we can actually just draw a line that goes through both of these intersection points and this point on the line. Just line them all up and draw that line right there. And once again, this here is perpendicular. We have constructed a perpendicular through a point. Okay, so now that we've constructed the perpendicular, we want to do a proof. And I'm going to do the proof of the first construction, the equilateral triangle one. And so before we can prove it, let's draw a diagram of the thing that we're proving here. So we need, before we construct a perpendicular through a point, a line that's perpendicular to another line through a point, we need those things. We need a line and we need a point. So here we go. Here's my line. Okay, I'll go ahead and call this line AB. And then I need to pick a point on AB, and I'm going to pick a point that's definitely not exactly in the middle. Let's go ahead and call this point here point P. So that's my point P on the line AB. So given line AB with point P. So we're given a line AB with some point P. And P could be at an endpoint, although then we'd have to do some extension. And so, yeah, you know, actually just for now, we'll just go ahead and assume that P is in the interior. So I'll say with P between A and B. So we'll go ahead and just not worry about the case where P is at one of the endpoints, and maybe I'll add that as an exercise. You know, do a proof for when P, and the construction for that matter, for when P is at an endpoint. And now our goal, so we want to construct a line perpendicular to AB through the point P. So given the line AB with a point P that's in the interior between A and B, construct the line that's perpendicular to AB through point P. Okay, so step one, Step one, as you saw in the construction, is to draw a circle. Centered at P. And so I'm not going to draw the circle, but I'll go ahead and count out. So waves 1, 2, 3, 4. So I'll count out, you know, here equidistant spaces. 1, 2, 3, 4. 1, 2, 3. Yeah, that's right. Okay. So draw a circle centered at P, and then it'll make, you know, maybe I will draw it out just so it's clear. So there's my circle. Okay. So we draw a circle centered at the point P. And that, of course, is rule number 4. Rule number 4 says I can draw a circle centered at any point. All right, step 2. Let's see, step 2 is we'll define 2 more points. So here and here, and we'll call that point C and D. Find C and D at the intersection points. I know I'm not specifying which intersections, but you can tell that from the diagram which intersections I'm talking about here. Maybe I'll put C inside the circle so it's very clear it's not another name for point A. So I'll put point C. I'll draw C right there. Okay, and our justification there, rule number 1 says you can draw or define a point anywhere. Step number 3, now we want to draw an equilateral triangle on CD. And so I'm not going to construct it, I'll go ahead and just try to eyeball it here. So I'm going to construct equilateral triangle. And this will be like C, let's see, what are we up to? C, A, E, this will be point E. So triangle C, D, E. And of course, that is brick number 2. Brick number 2 says I can construct an equilateral triangle. So brick 2. And let's go ahead and draw it in here. Okay, and now step 4, we are going to draw the line EP. I'm going to draw EP, and that is rule number 2. Rule number 2 says I can connect any 2 points with a line. All right, let's draw this in here. There we go. Now let's look at what we have here. Our goal is to prove this is a right angle. Now, based on the construction, I know that this is equal to this. Based on the fact that it's equilateral triangle, I know that equals that, and then EP is itself. So let's go ahead and get these facts down here. So step 5, CP equals PD. So this is equal to that. And that is based on the definition of a circle. Furthermore, EC is equal to ED. So EC is equal to ED. And that's the definition of equilateral triangle. And now, because this length here, EP, is just itself, so it equals itself, I can say that this right here is equal to this right here, these 2 triangles. So step 7 is to say that triangle ECP is equal to triangle EDP and therefore this angle here is equal to this angle here. So EPC, so and angle EPC is equal to the angle EPD. Okay, our justification for that is the fact that this side is equal to this side is equal to this side is itself. So by side, side, side equaling side, 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 I say that the triangles are equal by side, side, side. And therefore, these angles are also equal. Okay, so now you may recall in our proof for the last one, in the previous video, when these 2 angles add up to 180 and they're equal to each other, they must be perpendicular. So I know there are a couple more steps in here, but I'm going to say by the proof of, let's see, what would this be called? So I'm going to actually add this one soon to, oh, and you can't see what I'm writing, can you? To brick number 4, because it's part of the line bisector. By the proof of brick 4, B4, EP is perpendicular to AB. And that is definition of perpendicular. And we are done. This would actually take a few more steps to really do it properly. And when we run into this situation where we're like, wait a second, I did these steps here, and now I would have to repeat those same steps here. What that indicates is maybe we actually need to make a new theorem and add it to our list of bricks. So we're not going to worry about that just yet at this point, but we do want to add to our list of bricks. So first of all, brick 4. Brick 4 was the line bisector, right? The fact that these two lines bisect, and then we added to it to show that not only was it a bisector, it was a perpendicular bisector. So let me see if I can squeeze that in there. So I'm going to modify this a little bit. It's a perpendicular line bisector. And now I have the perpendicular through a point. Now, let's see, what did that depend on? It definitely depended on brick number 2, depended on some definitions, depended on the side. So now we're at the point where it doesn't actually depend directly on these. I just used the same steps from the proof. So maybe we need to start using arrows here. So from the equilateral triangle, we get that brick. So this is brick number 5. So we'll say perpendicular through, hang on, let me write this properly. Perpendicular through a point. Now, obviously, I know I'm really abbreviating here, but you get the idea. So there's a brick. It rests on the equilateral triangle, but it doesn't actually rest on top of these. So I'm going to put it next to there. Okay, that took a minute. So the next video, we're going to be looking at dropping a perpendicular from a point down to a line.